Okay, I would like to go over problem number 7 from section 5.2 in the textbook, which is a practical example of using the error formulas in order to figure out how many times you need to subdivide the interval when you're doing a numerical estimate of an integral. So, first of all, the integral they're trying to they're applying this to is the integral from 1 to 3 of log x dx. Okay, so I thought we'd just work out the exact value so we have something to compare our estimates to later. So the antiderivative of log x is x log x minus x, evaluated between 1 and 3, and it's pretty simple. So it turns out to be 3 log 3 minus 2, which is 1.295836866. And the challenge for us is to figure out what n has to be, n being the number of subdivisions, the number of intervals, in order for the numerical estimate to be within 5 times 10 to the negative 8. So that means we've got to get the this many digits accurate, basically. Or maybe I could say, oops, what have I done? Oh, there we go. Okay. Maybe I could say what we need is to get this many digits accurate, right? And the question is how many subdivisions do we need in order to do that? Okay. So first, let's do it with the trapezoid rule. First of all, note that for the trapezoid rule, we're going to need the first derivative. Remember the first derivative up here. Let's see, if our function f is log x, then f prime is 1 over x, right? So we'll need that in a minute. And the rule I'm going to use, or rather the error formula I'm going to use, is what's called the asymptotic error formula in the textbook. It's equation number 5.32. And it's a little easier to use than the other one. Also, it usually gives better results. I think it does in this case. So let's see. So the formula says that, oh, by the way, this guy over here, this notation simply means the error in the trapezoid estimate, the T is for trapezoid, sorry, there we go, okay. When you subdivide the interval into n equal pieces and apply it to the function f, right? So that's what the function f is. And then the formula says over here that it's approximately equal to, oh, but let me just emphasize, I did it again. Let me just emphasize oh God, I'll get the hang of this program eventually, don't worry. Let me emphasize, this is only an approximation, this is not exact, right? But it's approximately equal to minus h squared over 12 times the difference between f prime evaluated at b and f prime evaluated at a. Okay, so in our particular case, of course, a is 1, b is 3, and f prime is 1 over x, so we plug all this in. Oh, by the way, the other thing we need to know is that, of course, the width of the interval from x equals 1 to x equals 3 is 2, and therefore h, the width of each subinterval, is going to be 2 over n. Okay, so I plugged in 2 over n for h here, right? Replaced h with 2 over n, and plugged in the formula for the derivative, and at the points when a is 1 and b is 3, so we get this, right, this guy, and then this further simplifies down to this, right? So that we get 2 over 9 times n squared. And so that's our estimate for what the error would be, right, with n subdivisions. Now, the requirement was that we wanted that error to be less than or equal to 5 times 10 to the 8th. So now we have to solve this inequality for n. Okay, that's not, ooh, I did it again. That's not hard to do. Just, I'll leave it as an exercise, but you can verify that n, therefore, is going to be exactly this. It has to be greater than or equal to the square root of 2 over 9 times 5 times 10 to the 8th. And so if you punch that into a calculator, I did it again. If you punch that into a calculator, it comes out to be about 2,108 subdivisions in order to get that degree of accuracy. Okay, so that's with the trapezoid method. It'll take over 2,000 subdivisions in order to get the required accuracy. Now, what about Simpson's rule? So there's a similar formula for Simpson's rule. Again, it's the asymptotic error, estimate of the error using Simpson's rule. That's what the S is for, with n subdivisions of the function f, right? And in this case, the formula, the constants are a little different. It's h to the fourth, minus h to the fourth over 180, and then the difference in the third derivative evaluated at a and b. Okay, did I mention this is, oops, did I mention this is formula 5.3 in the book? Okay. 5.36 in the textbook, right? Now for this we're going to need the third derivative. Recall that the first derivative was 1 over x, so the second derivative is going to be negative 1 over x squared, and the third derivative is going to be 2 over x cubed. Okay, so we'll need those. Plug everything in. Again, for h, I'm going to substitute 2 over n for h. So in this case, substituting that in 2 over n for h, it gives us 16 over n to the fourth. The 180 is there, and then you plug in the values 1 and 3 into the third derivative, right, and evaluate that here. Okay, and then you do all the arithmetic, and it comes out to be this mess. It's 208 over 1215 times n to the fourth. Once again, the requirement is that this estimate for the error has to be no greater than 5 times 10 to the minus 8th. Once again, we solve for n. Easy to do. We get n equals, or rather n is greater than or equal to the fourth root of 208 over 5 times 1215 times 10 to the 8th. And if you crunch the numbers on a calculator, it comes out to be 43. One thing, though, for Simpson's rule, you have to have an even number of subdivisions, right? Because we pair the subdivisions in order to get 3 interpolation points that we can use, right? Because in principle, we're using 3 interpolation points for each segment, so we have to pair up the segments in order to get 3 interpolation points. So I'm going to bump that up to 44. So it seems like we're going to need 44 subdivisions in order to get the desired degree of accuracy with Simpson's rule. That's quite a dramatic difference, isn't it, right? From the previous, from 2,100 subdivisions to do it with the trapezoid rule, and only 44 subdivisions to do it with the Simpson's rule. So you can see how much more powerful Simpson's rule really is. Okay, next thing I want to do is I want to try this out on MATLAB and see if the prediction is valid. Now what I'd like to do is just try that out on MATLAB. I discovered something a little disconcerting. I discovered that when I used the trapezoidal f and Simpson f functions, they seem to be giving inexact results, and I don't understand why that was. So what I did was I rewrote those two functions. Well, I simplified them. Instead of writing them so that we got 9 different estimates of the integral, I just rewrote them so it only give 1, right? So the new version is called trapezoidal f1 and Simpson f1, and I've uploaded those to Canvas, to the Canvas module. And that seemed to work better for some reason. I haven't yet figured out why the other function was giving incorrect results. But anyway, let's try this. So, yeah, let me set the format again to long, and then let's just try this. So we found that the trapezoid method, trapezoid f1, okay. The integral from 1 to 3, it should only be, well, it should be necessary to divide it up into 2,108 separate subdivisions, subintervals, in order to get a sufficiently accurate result. Well, let's see if that works. So we're integrating the log function. Okay, let's give it a shot. 1.2958. I think that's correct, right? In fact, why don't I just redo the calculation? It was 3 log 3 minus 2, right? So yeah, so it seems that this is accurate up until here. It looks like it's, yeah, it's within 1, 2, 3. Yeah, it's within 5 to the 10 to the minus 8th, right, of the correct answer down here. Okay, so that looks good. Now let's try it with the Simpson method. And remember, for the Simpson method, it seemed that we only had to do it, what, 44 subdivisions in order to get an equally accurate result? So, did it work? 1.295682. Yes, it did work, right? Because that's 1, 2, 3, 4, 5. Yeah, that's right. That's accurate to within, also accurate to within 5 times 10 to the negative 8. Okay, so that's nice. The formulas were pretty easy to use, and they gave pretty accurate results. Okay, I want to show you how to use the other formulas, just for completeness. The problem in the textbook did not ask for it, but I would like to just try it out with the other formulas, see how they work. So it seems that, yeah, I wanted to show you the how the other formulas work. So the other formulas are, in theory, exact, but they make use of the mean value theorem, so they involve this number c over here, which we don't know. Right? We can't know exactly what c is. We just know that c is some point somewhere. Oops, I did it again. Somewhere, I did it again. Somewhere in the interval from a to b. Right? That's all we know about c. Notice it has a similar characteristic. It's minus 8 squared over 12, but then instead of multiplying by the difference between the third derivative at the limits of integration, we just take b minus a, the length of the whole interval, and times the second derivative evaluated somewhere on that interval. Okay, so plugging everything in here, now notice that in this case we need the second derivative. As you'll recall, the second derivative, where was it? Oh, it was over here. The second derivative was this, was minus 1 over x squared. So using that and evaluating at c, we get this. Plugging in h equals 2 over n, we get this. The length of the interval is 2, so b minus a is 2. Combine everything and simplify it down, you get this. Right? So that's our expression for the error. The trouble is we don't know what c is, so we have to make the worst case assumption of what c might be. And worst case assumption is that c could be 1, right? Because c appears in the denominator. So the worst case is when c is small, right? And therefore on the interval from 1 to 3, the worst case would be when c equals 1, right? So that's when this, I did it again. That's when this is maximized when c equals 1. Okay, so in other words, the worst case scenario is the error might be as big as 2 over 3 n squared. So again, our requirement, I did it again, our requirement is that the total error be no greater than 5 times 10 to the minus 8. So we solve this equation, we get this again, and it comes out to be 3,651, so it's greater than the other estimate. The other estimate was a bit better. It turned out it was adequate to do 2,800 subdivisions. That gave us a sufficiently accurate answer, but the difference is that one is not guaranteed to be correct, whereas this one is. We're guaranteed that if we do it 3,651 times, that we will definitely achieve at least the desired level of accuracy. Whereas with the other estimate, it's likely but not certain. Okay, if we do the same thing for Simpson rule has a similar error formula. In this case, it's negative h to the fourth times b minus a over 180 times the fourth derivative of the function evaluated at some point c. Once again, c is somewhere in the interval from a to b, we don't know where, and the fourth derivative is actually negative 6 over x to the fourth power. Right? So we'll need that. So you plug everything in, including you plug in n over 2 for, 2 over n for h, and you get this. And simplifying it down and considering the worst case scenario, which is still when c equals 1, we get this formula for the maximum of the error, right? That's an upper bound for the error. And then we want to set that formula less than or equal to 5 times 10 to the negative 8. And solving for n, we get this. And it turns out that n has to be at least equal to 68, right? So worst case scenario, you can definitely achieve the desired level of accuracy with 68 subdivisions. Again, what we saw with the previous estimate was that very likely you can do it with 44, and in fact it did turn out we were able to achieve the desired accuracy with 44 subdivisions, but that wasn't guaranteed. This is. We know we can do it with 68 subdivisions. Okay.